This is a final run through of the key topics for the foundation tier of AQA GCSE Combined Science Physics Paper 2 in 2022. In other words, I'm missing out anything that is in the not assessed section of the advanced information, and all of the major topics are on green slides. I also won't be going through all of the equations in depth because you'll have the equation sheet. Before we get started with the physics content, just some general advice. Make sure that you have a black pen and that you're writing inside of the boxes because your paper is going to be scanned and that's how it will scan best. For all of your calculations, watch out for sneaky units. So things like for all of the different calculations you do, mass needs to be in kilograms, but it's very likely that they might give you a question where they put it in grams, so you'd need to divide by 1,000. For extended response questions, bullet points are great. There are no marks in GCSE Science for writing in paragraphs or full sentences, so just make your life and your examiner's life easy. If you see the command word evaluate, you must compare both sides of the information and you must write a conclusion. If you have to write a method, say for one of the required practicals, then think about, does it have a logical flow to it and will it actually allow you to have valid data? Remember that lots of general working scientifically principles are going to be assessed in these papers as well. So make sure that you're confident naming your variables, that you know what the difference between repeatable and reproducible is, that you know that the resolution is the smallest measurement or the difference in measurements that you can detect with your equipment, that computerized methods are accurate, rapid and sensitive, and also watch out that when you're drawing graphs, if you draw a line of best fit, it doesn't have to be a straight line, even though they tell you that for GCSE maths, even for A-level maths, that's not true. So if your data curves, your line should curve too. When we think about errors, systematic errors are caused by equipment that isn't properly calibrated. So say, for instance, your scales always read ½ kilogram light, and therefore every time that you write down a measurement, you'd need to add ½ kilogram to it. Whereas random error is caused by a lack of precision, or just the fact that a value is kind of changing over time. So something like the temperature in the room isn't actually constant. And so the way that you get around that is that you repeat the measurements multiple times and you use those repeats to calculate a mean. It always seems to come as a surprise to students that actually there are a lot of marks for maths in the physics paper. There are supposed to be 30% of the marks. And if you're looking at this far enough in advance and you have the specification handy, then you can find all of these listed in chapter 9. But basically any of these could also be assessed in the paper. Another thing that often trips up students is forgetting to convert between the units. So making sure that when you do a calculation, all of your quantities are in their standard international units. And so just be aware that all of those conversions are by factors of 1,000. As you know, in 2022, you are going to be given the equation sheet, which you would normally have to memorise. But bear in mind that that equation sheet only contains each equation in one particular format, and also it doesn't tell you what any of the units are. So you still need to pay a bit of attention to this. So strangely, the first few equations on the sheet are actually ones that you don't need until paper 2, so we're going to ignore those. But one thing I would spend a little bit of time at the start of the exam doing is jotting down the units for the equations that you might need to use. First up is energy. So anywhere that you see energy, but also anywhere that you see work, which is just a type of energy, it's always going to be in joules, making sure, of course, that you have a capital J. Speed is in meters per second, and mass is always going to be in kilograms, and that comes up in several different equations. Height should be in meters, power should be in watts, and time should be in seconds. What else have we got? Charge flow is going to be in coulombs. Potential difference is basically just another name for voltage, so we can put that in volts. Current is in amps, and resistance is in ohms. You've also got density in kilograms per metre cubed, although this is one of the only ones where it doesn't always have to be in its SI units. So they could give you masses in grams and volumes in centimetres cubed and ask you to work out in density in grams per centimetre cubed, but normally we'd have volume in metres cubed. The first topic in physics paper 1, and it is a major topic, is energy. We start off talking about systems, which is just another name for an object or a group of objects. But systems can store energy in a number of different forms. So we have magnetic stores, kinetic stores, which is how energy is stored in a moving object, thermal stores, so those are hot objects, gravitational potential, if an object has been raised through a gravitational field, chemical stores, elastic potential, that's where we've got something that's been stretched or squashed, electrostatic, so that's the attraction between positive and negative objects, and nuclear stores. Then we can also talk about energy being transferred between those stores, so changed from type to type. And that could be by heating because of a temperature difference, mechanically, electrically, or by radiation. So just remember that light and sound are not stores. You can't store energy as light, but you can transfer energy in the form of radiation, which could be light or sound. Now, conservation of energy comes a little bit later in the spec and it's not a major topic, but I find it kind of hard to talk about these transfers without talking about conservation of energy. So that's why this slide is so early. So conservation of energy just means that in a closed system, in other words, in a system where no matter and no energy can get in or out, then energy can't be created and it can't be destroyed, it can only be transferred. So we can go from one store to a different store, but the overall amount of energy must remain the same. We also need to know that energy is always measured in joules with a nice capital J. So now we go through a series of calculations thinking about some of these different stores of energy. And as you know, you are going to have the equation sheet, so you're not going to need to memorise the equations, but you are still going to need to know what all of the different units are and also to be able to solve calculations with them. So for instance, gravitational potential energy is energy gained by raising an object against the action of a gravitational field. And a typical question might ask you how much gravitational potential energy you transfer to a 5 kilogram dumbbell when you lift it by 1.5 meters. And they would need to also tell you that on Earth the gravitational field strength is 9.8 newtons per kilogram. So the first thing I'm going to do is write down the equation from the equation sheet to show them I've selected the right one. Then I'm going to rewrite it below, but adding in the numbers in the right places. And so the way I know which number goes where is by looking at the units. So for instance, mass is always in kilograms, so the mass is going to be 5 because the 5 has kilograms after it. So I put in my 5 there, my 9.8 for gravitational field strength, and my 1.5 for the height, making sure that it's definitely in meters. That's a really easy, sneaky trick. So then if I multiply all of those together, I get 73.5 joules. Job done. Next up is kinetic energy. This is a little bit of a harder calculation to use because it has a squared in it. Watch out for the fact that that squared is only talking about the v, which represents velocity or speed. So that's the only bit that you're squaring. You're not squaring the whole thing. So again, a typical question might ask us how much kinetic energy an object has. So here I'm going to substitute in all my numbers and then multiply them together to get the final answer. Our next store is elastic potential energy. So this is where we've got something that's been stretched or squashed. Now, one of the mathematical skills that was in that list we looked at was about rearranging an equation to change the subject. But actually, if you look at any of the AQA mark schemes, they seem to prefer you to substitute your numbers before rearranging. So if we got a tricky question like this, which asked us to work out K, the spring constant, then I wouldn't actually rearrange this equation in order to make K the subject. What I would do is write it out, putting in the numbers they've given me. So 4,500 is the amount of energy, and then the extension is 3, so 3 is squared. And then I would just solve it for K exactly like I would if this was an algebra question in maths. So that would give me an answer of 1,000. Next up is specific heat capacity. So capacity is a concept that you meet in primary school, and it means the maximum amount of something that an object can contain. So we use it for jugs and things to say how much liquid we could fit in them. Heat capacity is the same idea, but just specifically thinking about energy. And then specific heat capacity refers to the fact that we're specifically looking at 1 kilogram and how much energy it takes to raise the temperature by 1 degree C. Required Practical 14 is all about finding out how you can measure the specific heat capacity of a material. So that could be a metal block, but it could also be a liquid. So basically what we want to do is to take this object and to heat it up and see how much energy it takes to heat it up. And then also if we know how much its mass is and we know how much the temperature has gone up by, then we can work out how much energy it would take to increase the temperature by just 1 degree if it weighed just 1 kilogram. So here we've got a metal block, that's what I'm measuring the specific heat capacity of. And I've got a balance so that I can measure the mass of it, because if it doesn't weigh exactly 1 kilogram to begin with, then I'm going to need to take that into account. Then I've got some insulation to wrap around it, because this experiment always gives you a value that's kind of too high for the specific heat capacity, because some of the energy that you're pumping into that block is actually being lost to the surroundings, and we want to minimise that, so we need to insulate it. Then I've got a thermometer, so I can measure the temperature change. The bigger the temperature change is, the more precise my final value will be. So I don't actually want to just heat it up by 1 degree C, because that probably won't be very accurate. So I'm going to heat it up by maybe 10 or 20 degrees C, and then divide my answer by 10 or 20 or whatever. I've got a pipette there, and that's just to add a little bit of water into the gap where the thermometer goes, because otherwise the thermometer isn't actually going to take the reading of the block accurately. I've got a heating element, so some kind of electrical heater which is used to heat up the block. And then you've got options. So here I've shown you with a voltmeter and an ammeter and a stop clock. And if you use this method, then basically what you do is you measure the potential difference across the block, you measure the current that's flowing, you use those together to work out what the power is, and then you use power together with time to work out the energy transfer. You could also use a piece of equipment called a joule meter, which would tell you the energy transfer directly. Power is a measure of the rate at which energy is transferred, or in other words, how quickly does it move from one store to another. So something very powerful can do a lot of work, i.e. transfer a lot of energy very quickly. A typical question might give you an appliance like a toaster or a kettle and ask you how powerful it is. So here I'd have my energy being 2000, and I can tell because energy is always measured in joules, and my time would be 4 seconds. Now watch out, because this is another place where the exam board could really easily give you that time in minutes or hours instead, and then you wouldn't get the right answer. So if I do 2000 divided by 4, I get an answer of 500 watts. We know that in every energy transfer, some of the energy is going to be transferred usefully. In other words, it's going to do what we want it to do, but some of it is going to be wasted. So it's going to be dissipated, or it's going to go into other stores other than the one we want. So a typical light bulb might transfer 1000 joules of energy, but only 100 joules of those might be transferred as light, as radiation, which is what we want the light bulb to do, and the other 900 joules might be wasted as heat. And so therefore my efficiency overall would only be 10%. There's a couple of different equations for efficiency, but they're basically exactly the same equation. It's just that one of them is in terms of energy and the other one is in terms of power. Also watch out for the fact that you could be asked to report your efficiency as a percentage rather than a decimal, in which case you just either use the percentage button on your calculator or multiply by 100. If the question asks you about the final store that their energy ends up in, there will almost always be some that ends up as thermal energy in the surroundings, and this is called dissipating. You should be able to discuss a number of ways in which we can reduce the wasted energy. So for instance, we can reduce the heat loss by insulating something. So that's particularly relevant if you're thinking about houses and how they might have loft insulation or double glazing and that sort of thing to help them be insulated. We can talk about the thermal conductivity of a material, so for instance looking at different kinds of brick, just regular brick versus breeze block, and the higher the thermal conductivity is, the higher the rate of energy transfer by conduction. So in other words, the better conductor it is, the faster it conducts. It's kind of obvious. You can also reduce wasted energy by reducing drag, by streamlining, so that's particularly relevant if you're thinking about boats or cars or just any kind of vehicle. And we can also reduce wasted energy by reducing friction. So that could involve using wheels, it could involve lubricating moving parts, and if those frictional forces aren't reduced, then they can cause energy to be transferred by heating. Next, we're on to 6.1.3, which is down in your specification as national and global energy resources, which basically just means places we can get energy from, ways we can generate electricity. So first off, we split these into renewable and non-renewable or finite. So renewable resources are being generated faster than they're being used, and that includes biofuels, tidal, hydroelectric, wave, wind, solar, and geothermal. Whereas non-renewable are being used faster than they're being generated. So these are the ones that are going to run out, like coal and oil and gas, so your 3 fossil fuels, but also nuclear energy. You should also be able to talk about how each of these energy resources can be used. So all of the ones that we've named are used to generate electricity in different ways, but additionally transport, so cars and lorries, can be powered by coal and oil and gas and biofuels, also nuclear power, although that tends to be when we're thinking about rockets and space travel and things. And then also in terms of heating, again, you can heat with those fossil fuels, and you can heat with solar power and with geothermal power. Discussing the advantages and disadvantages of these different energy resources is a prime opportunity for a 6-mark question. So remember, if it comes up, you are going to need to evaluate, you are going to need to write a conclusion and say which one you think is best. Key advantages to think about are whether or not they're renewable, in other words, they won't run out, whether they're cheap, whether they have carbon dioxide emissions, because as we know, carbon dioxide is a greenhouse gas and it's leading to further global warming, so that's not a good thing. Whether they're reliable, so for instance, you can't use wind power if it's not a windy day, you can't use solar power if there isn't any sunlight, so those would make those kinds of generating electricity unreliable. And also whether it's possible to use them anywhere in the country. So for instance, some of these methods of generating electricity, you need to be by the coast, you need to be by the sea. And then disadvantages would include carbon dioxide emissions, being non-renewable, being unreliable, the idea of noise and visual pollution, and also if we're thinking about nuclear power, even though it has a huge amount of energy stored in it and therefore has lots of advantages from that point of view, it produces radioactive waste that needs to be disposed of, and also there is a small risk of a nuclear accident. Topic 2 in physics paper 1 is electricity. So the first thing that you need to know is all of the circuit symbols for the different components. Now the ones that people particularly tend to fall down on are getting your arrows the wrong way around for LEDs and LDRs. So it might help if you remember that an LED is a light emitting diode. In other words, it's giving out the light, so the arrows are going away from it, whereas an LDR is a light dependent resistor, the light is coming in. Also watch out for drawing your resistor and drawing your fuse. It's really common that people draw the line for the wire and then draw the resistor on top of it, but of course if you don't rub out the line, then what you're drawing is a fuse, which is a completely different component, so watch out for that one. We then talk about current and potential difference. So current is the speed of the flow of charge around a circuit. But just to make you aware, even though it's electrons that are flowing, actually conventional current flows in kind of the wrong direction basically, because when current was first discovered, people thought that the particles that were moving had a positive charge. And so we've carried on using that system, even though we now know that it's electrons. Potential difference is about the amount of energy being transferred. So we could measure it on either side of a cell or a battery and see how much energy is being given to the electrons as they go past, or we could measure it on either side of a component like a lamp and see how much energy is being transferred from the electrons to the lamp. Required Practical 15 is looking at the IV characteristics, in other words, the current and the potential difference of a wire of different lengths and also of resistors in series and parallel. So basically for each one of these, you just need a simple circuit and it needs to contain an ammeter, which must be in series because otherwise it won't work, and a voltmeter, which must be connected in parallel, otherwise it won't work. Then you have another different required practical in which instead of looking at the current and the potential difference across a wire or resistors in series and parallel, we're now looking at various components. So this includes a wire at constant temperature, a filament bulb, and also a diode. These are all IV graphs. So I is current and that's on the y-axis, and then V is potential difference, which is on the x-axis. The first one is for a wire at a constant temperature, or what we call an ohmic conductor. And for this one, you're going to see a directly proportional relationship. In other words, it's going to be a straight line graph that goes exactly through the origin, which is 0, 0. Then the difference between the filament lamp and the ohmic conductor is that whereas the ohmic conductor is at a constant temperature, the filament lamp is getting hotter as it's turned on. And so what we see is that the bigger the potential difference is, the higher the resistance is because the wire is getting hot. And so even though you're increasing the potential difference, the current doesn't continue increasing by the same amount. So we get this slightly S-shaped curve. And then finally we have the diode, and the most important thing about the diode is that it only allows the current to flow in one direction. So you're not going to see any graph at all below the x-axis. But it's also worth noting that when the potential difference is very small, no current will flow. So it doesn't just start going up straight from the origin, it kind of goes flat along the x-axis for a little bit and then it kicks up. Now, these two graphs are different to the last ones. So the last ones were IV graphs with current and potential difference. These ones have resistance on the y-axis, and then on the x-axis they have whatever is pertinent to this particular component. So on the left we've got a light-dependent resistor, and the point of a light-dependent resistor is that the brighter the light is, the less it's resisting. So you could use this, for instance, to turn on a radio in the morning. As the sun comes up and it gets lighter, there's less resistance, so then the current can flow and the radio turns on. And then on the right, we have a thermistor, and as the temperature increases for this one, the resistance goes down. So that's different to a wire, it's opposite of a wire. Then we get series and parallel circuits. So in a series circuit, there's only one path that the charges can follow. So everything goes in the same direction, everything follows the same path. Whereas in a parallel circuit, there is a point or a junction where the current splits. So some are going to go past one light bulb and some are going to go past the other light bulb. For the series circuit and the parallel circuit, you need to be able to discuss both the current, so how quickly the charges are moving, and also the potential difference, so the amount of energy that's being transferred. So if we think about the series circuit first and current, we've said that current is about how many charges pass a particular point per second. And the image you want to have in your head is that this is like a traffic jam. There are no gaps. If one moves forward, the ones behind it move forward, and everything is going to be moving at exactly the same speed. So because there's only one loop and all of the charges are going the same way, they're all going to go at the same speed. So the current anywhere in that series circuit will be exactly the same. I can put my ammeter wherever I like. Now in the parallel circuit it's a little bit different because they are still going nose to tail like it's in a traffic jam, but when they get to point A, they're going to split. So if those branches are identical, then half of them will go one way and half of them will go the other way. Now the branches might not be identical. It could be that 2/3 of them go one way and 1/3 of them go a different way. But we're always going to have a situation where the current in those two branches will add up to be the same as it would have been before it split. So that's the difference between series and parallel in terms of current. If we now think about potential difference, that's about how much energy is being transferred. So imagine that as these electrons are going past the cell, they're picking up some energy. In the series circuit that I've drawn here, they're going to have to split that energy between the two light bulbs because they're going to go past both of them. So each bulb is only going to get half of the energy that was picked up from the cell. But in the parallel circuit, each charge is only going past one of the light bulbs. So it doesn't need to save half of its energy to give to the other bulb, it's all going to be given up in one go. So whereas for current, we had it was the same everywhere in the series circuit and it's split in the parallel circuit, for potential difference, it's going to be the other way around. In the series circuit, the potential difference is going to be split between the two components, whereas in the parallel circuit, each component is going to get the full potential difference. And that's why the light bulbs in a parallel circuit are going to be much brighter. Finally, if we were thinking about resistors, you should be able to describe that in a series circuit, to work out the total resistance, we're just going to add up those resistors. So say if I had 3 resistors and they each had a resistance of 2 ohms, then the total resistance would just be 6 ohms. You literally just add them together. Whereas in a parallel circuit, the total resistance is going to be less than the resistance of the smallest individual resistor. So to actually work it out, we say that 1 divided by the total resistance is going to be 1 divided by each of the individual resistances. But basically the most important thing is that when you add all of those up together, you're going to find that the overall resistance is less than any of the individual ones. Finally, for the electricity topic, we get to the national grid, which is the system of cables and transformers that links power stations to consumers. Now, in between the power station and the national grid, and then the national grid and your house, there are these transformers. And the point of the transformers is to step up and then step down the potential difference. Now, the reason for that is the consumers need a certain amount of electricity. They need a certain amount of power. Now, power is a function of potential difference and current. In other words, in order for us to get that power to the consumers, we either need the electrons to move really, really fast, or every electron to carry a lot of energy. If the electrons move really, really fast, in other words, if the current was high, then the wires would get really hot and we would waste a huge amount of energy. So it's a much better idea for each electron to carry a lot of energy. And that's basically what we mean by a high potential difference. So the first transformer, the step up transformer, is going to increase the potential difference to a really, really high potential difference, like 400,000 volts or so. And then the step down transformer at the other end is going to step it back down to 230 volts so that it is safe for domestic customers. Our third topic in physics paper 1 is about states of matter, so solids and liquids and gases. So we start off with a bit of the particle model. So in a solid, all the particles are packed in this regular structure. In a liquid, they're close together, they're all touching, we don't have big spaces between them. And then in a gas, the particles are separated by large distances. If we then think about the forces, in a solid, there are these really strong forces that are holding the particles in place. So they're vibrating in fixed positions, but they're not moving past each other. In a liquid, the forces are a little bit weaker, but they are still there. They are still maintaining contact, but the particles are able to pass over each other. And then in a gas, there are really weak forces, but the particles are able to constantly, randomly move. So we've covered most of this already. We've talked about the arrangement and the forces and the movement, but crucially, this means that for solids, it's relatively difficult to change their shape. For liquids, it's pretty easy to change their shape. We can pour them into a different container, but they are virtually incompressible. In other words, you can't squash them. Whereas gases, they can expand to fill a space, and they're also very easy to compress. You should be able to describe all of the different changes of state, so melting, freezing, boiling, evaporating, condensing, and sublimating, which is the one that people forget. So that's going straight from a solid to a gas, like carbon dioxide likes to do. And you should be aware that this is a physical process and that mass is conserved. So if you take a kilogram of ice and you melt it and then you boil it, you would get a kilogram of steam. So actually, I suppose my diagram isn't great because it makes it look like I've lost some particles somewhere, whereas really my box for gases should just be a much, much bigger box with the same number of particles in it. You should be aware that this is a physical change and that physical changes are different from chemical changes, because if you reverse the change, so say if we cool something down, having heated it up, you get the original properties back. So if I took my steam and I cooled it down until it was below zero, then it would turn back into ice and the ice would be exactly the same as it originally was. Once we've established what solids and liquids and gases are like, then we can start to talk about density. So this is a measure of the mass of a substance if we have a particular volume of it. In other words, how much does a metre cubed have a mass of? So in order to calculate it, we take the mass and we divide it by the volume. And this is quite a nice one because if you remember that mass is in kilograms and volume is in metres cubed, then the units for density are fairly obvious. Now, the required practical for density requires you to determine the density of regular and irregular solid objects and also liquids. But for all three of them, you're going to need to measure the mass, which you would obviously do using a balance, and then also measure the volume. And this is where it's different when we look at the liquids and the regular and irregular solids. So for liquids, it's quite straightforward. You measure the volume using a measuring cylinder. So you just put it on the balance, zero the balance, pour your liquid in, and then see how much there is there, and also look at what the mass is. Nice and straightforward. For regular objects, you would either use a ruler or some calipers, as I've shown here, because they will allow you a greater degree of precision. And then you can work out for a cuboid that its volume will be the length multiplied by the width multiplied by the depth, or if it's a cube, then of course those are all the same as each other. So then again, you would need to measure the mass of your object using a balance and use this together with the volume that you've just calculated to work out the density. And then for irregular objects like my keyring here, you need to use this piece of equipment, which is called a displacement can, or you might also hear it called a eureka can. So you need to fill it up with water right the way up until water is coming out of the spout. And then you're going to fully submerge your object into that displacement can. And as you do so, it will displace some water. It will push water out of the spout. So you catch that water in a measuring cylinder, and then you can measure the volume of that water. And this works because the volume of the water will be equal to the volume of the object. And then again, we need to measure the mass of the object using the balance, and then we can calculate density. Then we move on to internal energy. So the energy that's stored in a system by the particles is called internal energy. So everything has internal energy, even if it's not moving right now. And internal energy is made up of two things. So the total kinetic energy of the system, in other words, the particles that are moving around, and the total potential energy of the system. As you're heating a substance, the energy stored within the system will increase, but this doesn't always get reflected by an increase in temperature. So if we take some ice and we heat it up, we actually see a graph that looks a bit like this, which might come as a bit of a surprise because you might expect the temperature to just go up all in one nice straight line. So what's actually going on here? Well, we've got this flat line here where the ice is melting, and another flat line here where the water is boiling. So whenever the substance is going through a state change, the temperature doesn't actually change. You can almost think of it like the substance can't multitask. Either it can get hotter or it can change state. It can't do both at the same time, assuming it's a pure substance. So the red bits of the graph here represent places where the energy is going into the substance and it's making the particles move faster. So if it's a solid, if it's my ice, then they're vibrating faster on the spot, and then if it's a liquid, they're moving faster past each other. And so the temperature is increasing as that happens. So if I want to know exactly how much energy it's going to take to do this, then we need to know the specific heat capacity, which we met earlier in the energy topic. And that tells us how much energy is needed to raise the temperature of a substance by 1 degree C. And then the green bits of my graph are where the state changes are happening. So here, instead of that energy increasing the kinetic energy of the particles, it's increasing the potential energy of the particles. And so that's where my state change happens. And if I want to know how much energy that's going to take, then I need to know about specific latent heat, which tells me how much energy is needed to change the state of 1 kilogram of a substance. Now, that's obviously not going to be the same amount of energy for melting it as for boiling it. So we have slightly different names. So we have the specific latent heat of fusion when a substance is melting, and the specific latent heat of vaporization when it is turning into a gas. So again, this is an equation with quite sensible units in that energy is going to be measured in joules and mass is measured in kilograms. So therefore specific latent heat is in joules per kilogram, which is nice and easy to remember. And then the final topic for physics paper 1 is the atomic structure and radiation topic. So we start off with this idea of isotopes. So these are different versions of an atom that have the same number of protons, different numbers of neutrons. And some of them are unstable. And so they give off radiation as they change to a form where they're more stable, and this may involve them turning into a completely different element. So we describe the rate at which that decay happens as activity, and we measure that in becquerels using a Geiger-Müller tube. There are 3 different types of radiation and they all ionize. So in other words, they turn uncharged atoms into charged ions by gaining or losing electrons. So our first kind of decay is called alpha decay. So an alpha particle is made up of 2 protons and 2 neutrons, which is exactly the same thing as a helium nucleus. So if we took a helium atom and we just pulled the electrons off it. So here I've got an unstable parent nucleus, and this alpha particle breaks off it, and we're left with what we call the daughter nucleus, which is now going to be a completely different element because it's got 2 fewer protons, and protons are what decide what element something is. So alpha particles are very ionizing. They're very good at turning other atoms into ions, but they're not very penetrating. You can basically think of it as they're really big, so they can't get through sort of pieces of paper and things. They've got a very short range in air because basically as they're travelling, they collide with air molecules and they just get stopped. They are deflected by an electromagnetic field and they can be stopped by a thin sheet of paper. Our second type of radiation is beta decay. So this is still a particle, but this time instead of a proton or a neutron, it's made of electrons, fast-moving electrons. And this often confuses a lot of people because they're thinking, but surely there aren't any electrons in the nucleus. So the way to think of it is to imagine that a neutron is just a proton with an electron stuck to it. And so what happens is that one of these neutrons turns into a proton, and in doing so, it loses an electron. So that electron gets kicked out there. So again, this is going to change the element that you've got because you've now got an extra proton that you didn't have before. So these beta particles are less ionizing than the alpha particles because they're smaller and they're also less charged. There's only 1 negative charge as opposed to the 2 positive on the alpha. They're more penetrating, so because they're smaller, they can get further. They've got a medium range in air. They're still deflected by an electromagnetic field, but in the opposite direction to the alpha particle because they're negatively charged instead of positively charged. And they can get through paper, but they can be stopped by aluminium foil. And then finally, we have our gamma decay, which is usually given out at the same time as the alpha particle or the beta particle. Now, gamma radiation is not a particle, it's an electromagnetic wave, and it's even less ionizing than the beta particle. However, it is more penetrating, so although it's less likely to ionize an atom, it's more likely to get to that atom in the first place. Gamma rays have a huge range in air and they're not deflected by an electromagnetic field, but they can be stopped by a thick layer of lead. So just to sort of summarise those, the alpha particle can be stopped by paper, the beta particle gets through paper but gets stopped by aluminium foil, and the gamma wave can keep going right until it meets a really thick layer of lead. Nuclear equations tend to scare a lot of people, but actually they're really straightforward as long as you think of that arrow as being like an equal sign and say that everything on either side needs to add up. So if you have alpha radiation being given off, then that's the same as a helium nucleus, so we can fill in the 4 and the 2. And then we need our sides of the equation to balance. So something plus 4 makes 219, something plus 2 makes 86, so we can fill in there 215 and 84. Now, the beta radiation tends to be the one that confuses people. The top bit is really straightforward. An electron doesn't have a mass that would feature in this. Obviously, it does have a mass, but it's so small that we don't write it down. So it just stays 14. And then the problem we have here is that people often try and do 6 take away 1. So just keep calm and remember the two sides have to be equal to each other. So 6 is equal to something take away 1. So it's going to be 7 take away 1. In any sample of radioisotopes, in other words, radioactive nuclei or radioactive atoms, they're going to decay over time, but you don't know when each individual nucleus is going to decay. That's a random process. But what you do know is that overall the rate of decay is pretty much constant. So we can work out this thing called half-life, and half-life is the time taken for the count rate, so the activity that you're reading off from your Geiger counter, to decrease by half. Or you can define it as the time taken for half of the atoms in the sample to decay, because it will be the same amount of time, because the reason that you're able to read it with your Geiger counter is that it's detecting those atoms breaking down. So it's basically the same thing and either definition is fine. So on a graph, it's going to look like this, and you're either going to have the number of atoms on your y-axis or activity on your y-axis. You treat it exactly the same. But basically what we're saying is that if we started off and we had a count rate of 20,000 becquerels, then in order to work out the half-life, I would say, well, how long does it take to get to 10,000 becquerels? And then I could read off on the x-axis the amount of time that that's taken, and that's my half-life. Okay, so here I've shown it as t. Now, I don't actually have to start at the start of the graph. I don't have to start at 20,000 becquerels, because if I started at any other number, I could still do the same thing. So if I went from 10,000 becquerels down to 5,000 becquerels, it would take me the exact same amount of time because that half-life doesn't change. And likewise, going from 5,000 to 2,500, it still wouldn't change. It's just a little bit easier if you start from your time is 0, because then the next point that you get to is exactly the time you're reading off. You're not having to do any subtraction. Now you might also get a question where you don't have a graph and instead they give you some numbers like this. So my little yellow box, it's not related to the graph, it's just a similar question but without a graph. So here we're asking, what's the half-life if it takes 24 days to go from 64,000 becquerels to 4,000 becquerels? So the trick is you need to see how many times has the activity halved. So we start off at 64,000, go down to 32,000, go down to 16,000, so each time I'm halving it. And then the crucial thing is that we're looking at how many times it has halved. So that's why I would always put these arrows in there, because otherwise you risk, people always end up counting the numbers instead and thinking it's 5. And this isn't 5, it's halved 4 times. So I know then that 4 half-lives is 24 days. So then how long is one half-life? Oh, I do 24 divided by 4, it's 6 days. Contamination and irradiation are both hazards of dealing with radioactive materials, but they're different to each other. So if you've been radioactively contaminated, then that means that there's the unwanted presence of materials that contain radioactive atoms. So in other words, there are atoms on you that at some point are going to break down, they're going to produce ionizing radiation. And so, at some point, it's like a ticking time bomb. You have become radioactive because these radioactive atoms are on you, and you could affect something else. And how hazardous that is going to depend on the particular type of atoms that they are, and whether they're going to release alpha or beta or gamma radiation, and what the half-life is, and all that sort of thing. Then irradiation is where we expose an object to nuclear radiation. So in other words, things like if you've got fruit and vegetables and you're irradiating them so that you can kill any pathogens that might be on them and stop them from going mouldy as quickly. And so if you do that, then the object that you're irradiating doesn't become radioactive itself. So it could be hazardous if it's a living thing to be irradiated. You know, you wouldn't want to be irradiated necessarily, but if you've irradiated some strawberries, then the strawberries don't become radioactive and there isn't any risk to anybody if they were to eat them. So that's it for the foundation tier of Physics Paper 1 of AQA Combined Science. I really hope that has helped you to feel a bit more confident about preparing for the exam and making sure that you understand all of that content. I'm wishing you so much luck, so just go and do your very best.